Good morning, everybody. Today we are going to discuss the last section of medical statistics in our course, which is correlation and regression analysis. But firstly, we need to finish by talking about the analysis of qualitative data. On the last lecture, we talked about quantitative data and analysis of quantitative data. Today, we will continue to talk about analysis using the special criterion of mathematical and medical statistics. And today, we will to talk about analysis of qualitative data. And and our next section is analysis of qualitative data. Yeah. So we choose the method of analysis according to a certain algorithm. Initially, we determine whether the samples and depend or not. How was on the last lecture? Firstly, we must think and we must choose what is the sample, dependent or independent. So if the samples are dependent, we have dependent samples, what happened? Then we look at the number of these samples. Yeah, how was on the last lecture? Firstly, dependent or independent. Secondly, what? How much samples we have in our analysis. If you have and if we have, or if there are two samples, then we can use the McNemar criterion for analysis. If there are more than two samples, so it may be 3 samples, 4, and many samples maybe, you and we must use coherence criterion. But it was about dependent samples. So, but what happened if our samples are independent? So, if again, we must see how much samples we have. If there are 2 samples, two independent samples, we can use Fisher's exact test or Pearson chi-square criterion for analysis. If there are more than 2 samples, so then we should use Pearson chi-square criterion. If we have 3, 4, or more samples. So, and what happened if we have 2 independent samples after choosing test for analysis? After that, we must necessarily calculate the odds ratio with the confidence interval or relative risk. It depends on what type of study we have. If our study is retrospective, such as a case control study, maybe we said about it on our last lectures, then we calculate the odds ratio. But if our study is prospective, such as a cohort study maybe, then we should calculate the relative risk. And in our course, we will only talk about the case when the samples are independent, which is bottom on the chart. So let's continue to talk. If we have 2 independent samples or 2 proportions, the rule of 2 proportions. For example, we are given 2 independent groups of irritable bowel syndrome patients with diarrhea or with constipation. The last example, we used this example on our last lecture. So we need to find out whether the proportions of patients with some trait are the same in these 2 groups. So, whether there is a relationship with gender, such as with manifestation of irritable bowel syndrome, is greater in men and which in women, for women and for men. So, this is done by making 4 field tables. You can see 4 field tables. Usually, I think you saw the name 2 by 2 contingency tables or just 2 by 2 tables. Yes, simple 2 by 2 tables. And this table is for this example, 2 or 2 table. The risk factor is there or not. The outcome is there or not. You can see risk factor or exodus or outcomes, So, and the amounts are counted, So, let's look at an example. And this example. You can see, don't forget about total of this outcomes and risk factor, and here the same. So, our example, we need to know if there are statistically significant differences between the frequency of individuals with constipation or diarrhea among men and women with irritable bowel syndrome. So, according to our data, out of 35 women, 10 have diarrhea and 25 have constipation. You can see a woman, irritable bowel syndrome, IBS, with diarrhea, 10 women, and with constipation, 25 women. So, total number of women, there are 35. So, what is about men? There are 27 men which have 20 for them have diarrhea and 7 with constipation. We made 2 by 2 table. This table, Next, what is the next? After that, we need to find out if the proportions of irritable bowel syndrome with diarrhea are the same in men and women. From our data, we may think there is a difference, but we need to generalize everything to the general population or population, we said. And to do this, we need to use a hypothesis testing criterion. After that, hypothesis testing criterion. What criterion we should use? The first criterion we will break down for this example is Pearson chi-square test. It allows us to evaluate the statistical significance of differences between 2 or more relative measures, maybe frequencies, maybe fractions, Its advantage is that it can work not only with 2 samples, but also in cases when we have several indicators. This criterion can be applied under certain conditions, like as a different criteria. There are some conditions where we can use this test, Pearson's chi-square test. So, when can we use this criteria? Only when our data is qualitative, and so the indicators to be compared must be measured on nominal or ordinal scale. Next is the groups to be compared must be independent. Independent samples. Nominal or ordinal scale. What is the next? Also, the groups to be compared must be independent, how we said, And what happened with dependent samples, For dependent samples, we will use other criteria. When we analyze 4 field tables, the expected values in each cell must be at least 10. This will be clear from the example. And when we analyze multi-field tables, maybe 2 by 3, 3 by 5, 5 by 10, 5 by 7, then the expected number of observations should not take values less than 5 in more than 20% of the cells. So this should also be paid attention to. Usually, no one analyzes such large tables manually, and statistical software packages indicate whether the conditions is met or not. Yeah. So let's see the example how this test is work. We on our department in our course we don't use the software. Yeah, we don't use the special programs. We use our hand, we use our pen and pencil, our calculator, and what especially our brain to understand, to best understand. Yeah, for best understanding of criteria. So let's look at an example how these criteria work. We need to calculate the expected frequencies because we have the condition that the expected frequencies must not be less than 10. We calculate them. For our example, let's see in our tables. Yeah, I think you see that all these tables very big. I have a confused. How can I do it? Students, it's not problem. Really, it's very simple calculations. Let's see. We have the values 35, 27, 30, and 32. You can see total numbers. All of them 62. We calculate the expected frequency of irritable bowel syndrome with diarrhea in women. How? 35 multiply on what? And what is about 35? 35 is A plus B in our table. And this is the sum of this line. We should multiply it on what? A plus C. What is about A plus C? A plus C and this total number. This is 30. After that, we should divide it by total of our line. And what happened? Divide by 62. And our answer will be 16.9. In women with constipations, what happened? Again, A plus B multiply on B plus D and divided by sum of the total. Yeah. So what happened? 35 again multiplied by 32 total number B plus D and divided by what? Divided by total number of these examples. Yeah. So 60 divided by 62 and answer will be 18.1. What is about men? Men with diarrhea. Let's see this line. Yeah, men with diarrhea. What happened? 27, this is C plus D. Plus, multiply, by 30. What is about 30? A plus C and divided by total again. Total is 62. And the answer will be 13.1. And the last, men with constipation. So will be 27 C plus D multiplied by B plus D. B plus D is 32 and divided by total 62. What happened? 13.9. And these turned out to be approximately the expected frequencies. This is expected frequency and frequencies, and especially approximated expected frequencies. And we see that all they are all greater than 10. Let's see again. 16.9, 13, 18, 13. This is more than 10. What happened? So we are entitled to use Pearson's chi-square test. We find the value of chi-square criterion using the formula shown on the slide. Here, the big formula, where the sum is in the total. Yeah, sum by sum. What happened? I think you think, oh, I have a confused again. How I can calculate it? It's very big. It's very complicated. I don't do it. No, students, it's very simple. Especially if the tables 2 by 2. Yeah, we have tables 2 by 2, so it will be really simple. In this formula, what is about O? O, students, is observed frequencies. Yeah, the first letter, observed frequencies. It's not expected. This is observed frequencies. And in the formula minus E ij. What is about E? E is expected frequencies, yeah? The first letter E, expected frequencies. So the first table, this table, shows the observed frequencies, but the second table shows us what expected frequencies. So let's consider the frequency of men with constipation is 7. Yeah, you can see. The frequency of men with constipation is 7. But we got an expected frequency greater than 10. How do we calculate He square test, yeah? The observed frequency minus expected frequency squared and divided by expected frequency, you can see. O minus E in square divided by E. And what happened? What we have after that? So 10 minus 16.9 in square divided by 16.9. This is for what? For women with diarrhea. What is the next? Women with constipation. What happened? 25 minus expected frequency 18.1 in square and divide by 18.1. The same with men with diarrhea and men with constipation. Let's see, 20 minus 13.1, put it in square and divide by expected frequency of diarrhea is 13.1. And the same for last column, for last point is men with constipation. What happened? 7 minus 13.9 and put it in square and divide by expected frequency 13.9. After our calculations, what happened? We have, yeah, that makes 4 elements, and after that we have the answer. But if the table is not 2 by 2, we will have more summands in formula when we calculate, yeah? So we should put every column, every point in every column. So in our situation, it turns out that the control value of He square criterion is 12.6. This number, 12.6. The number of degrees of freedom in this case is calculated using this formula. K minus n multiply on n minus 1. So, in our example, K is 2 minus 1 and n is 2 minus 1, so the answer will be 1. And in our case, here we can say that the answer will be 1 degree of freedom in our example. So, what is the next? Next, according the Pearson He square tables, we look for our critical values. After that will be critical values. Yeah, we calculated control value. After that, we should find critical value in special tables by criterion. Yeah, and what is the next? Compare these numbers. So let's start to do it, and we look for our critical values. Yeah, for our degree of number of degree of freedom. Yeah, so we see that our control value, what happened? Our control value, 12.6, is more than the critical value for the significance level 0.01. Accordingly, the null hypothesis is rejected with the confidence level 99% and the dependence of irritable bowel syndrome frequency with constipation and with diarrhea depending on gender is statistically significant. Again, we have significant frequency of significant samples when we have irritable bowel syndrome frequency with constipation and with diarrhea depending on gender according our example. And what happened? With 99% confidence, we can say that the incidence of diarrhea and constipation is different between men and women. If we represent this graphically, we can see the constipation as a manifestation of irritable bowel syndrome is more frequent in women. Let's see. Female and women, is male is man, we say about gender. So let's see that in our graph, in our column, what happened. Irritable bowel syndrome is more frequent in women, in women with constipations. Let's see, with constipations, this number. It show us for best understanding, and we can say about it for other people, for other students, if we calculate or if we do our tests. For example, with these examples or maybe with other examples. So, and what is the next way to check the difference in frequencies? Is the Fisher's exact test. Nextly, the conditions for its application. So what? The variables to be compared must be measured on a nominal scale and have only two values. What is next? The advantage of this criterion is that it's suitable for comparing very, very small samples. That's what it was designed for. But its big plus, this really big positive part, is that it calculates the level of significance, or we can say the probability of our error. Level of significance, this is the probability of our error. You don't have to compare anything to tabulated values. But the main disadvantage of this criterion is very, very, very large calculations. So again, let's look at an example. I randomly removed many values from the previous example, leaving only 26 values. Why 26 values? For small calculation students, only for small calculations. The frequencies are very small, and the significance level is calculated using formula on the slide. You can see this big formula. We use the factorials everywhere. You can see here, everywhere, factorials. So you should know from high school or from your school, secondary school, what a factorial is. For example, let's remember. For example, what is about 5 factorial? What is this? We should multiply 1 by 2, multiply on y, on 2, on 3, on 4, and on 5. So, and even in our case, where the frequencies turned out to be quite small, the calculation in the formula is very, 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 very large. I used the rules of factorials, and calculated without calculator. So if we know the special rules of factorial, these calculations will be simple. But if we use calculator, simple calculator, not engineer calculator, you have many complicated calculations, and so maybe a mistake. So you should do these calculations with very slowly firstly, and be careful with these calculations to calculate it without mistake. So the result of this is the number 0.021. This value. What happened? After that, we can see that it's less than accepted level of significance of 0.05. So we can conclude that the frequencies of irritable bowel syndrome with constipation and with diarrhea depend on gender with a 97.9% confidence level. The advantage of the method is that we can accurately calculate the value of significance level. It isn't called the exact criterion for nothing, but its main disadvantage is in large calculations. And for large samples, you can often not have enough computing power of the software package. In such case, when there is no possibility to calculate the exact Fisher criterion, consider Pearson chi-square criterion. It's also good and does not require such huge calculations. Yeah, really huge calculations and maybe situation. When you have many samples and your soft package can't calculate it, and so I recommend to you to use what Pearson chi-square criterion. You can use it in this special situation. And in the case of 2x2 contingency table analysis, and when the data are binary, it's highly recommended to do an odds ratio or relative risk calculation depending on what? On the type of study. What is about odds ratio? Yeah. Let's start with the odds ratio without risks. Yeah. So, what is about odds ratio? This is a ratio of the odds of a certain event for the first group to the odds of the same event for the second group. The formula on the right is O1. To the odds here, this is, what is this? First group for O1 and second group O2. Formula is O2. So the result is the formula below. You can see the result. Odds ratio, what is this? O1 divided by O2. And how can we calculate it? You can see on this slide. Yeah, I think you know that. Again, big formula, again, big calculations, and again, I have confused. No, students, again, very simple calculations. And the advantage of the odds ratio is that it allows us to estimate the relationship between a particular outcome and a risk factor, and it allows us to compare the groups of subjects by the frequency with which a particular outcome is detected. We can use odds ratio under certain conditions again. When the data must be nominal, firstly. Secondly, and data must be binary and only 2x2 tables, and groups must be independent. And the odds ratio is counted in retrospective studies, such as a case control. In addition to the odds ratio itself, but sure to indicate the limits of the 95% confidence interval. Because we are going to generalize everything to the population, to the general population. The lower bound is calculated as follows. It's the number E. What is about E? E is 27, yeah? In what power? In the power of the natural logarithm of the odds ratio minus 1.96 and multiplied by the value under the square root, yeah? Under this sum. The lower bound is the same, except the formula has a plus sign, yeah? Lower boundary and upper limit. So, let's look this criterion by the example again. So, in our example, the table shows inherited defects of the hemostasis system, either present or not. And as well as data on the history, whether there was an unfertile pregnancy, so uncomplicated pregnancy. Yeah, what happened? The table shows the frequencies. You can see the table. Hemostasis system, defects of the hemostasis system, and uncomplicated pregnancy, yes or not, and problems, yes or not. And we calculate the odds ratio using the formula, using this formula. How? We should A multiply by D and divide it by multiplication, result multiplication B and C. So A, D, B, C. Oh, sorry, yeah, A, D, B, C. We have a 18. Odds ratio is 18. The lower limit was what? This number. This is a lower limit with minus, yeah? We have in the formula with minus, and result of this calculation is 3.59. And the upper limit is 90.38. It turns out that the odds of an understanding pregnancy, or we can say uncomplicated pregnancy in a pregnant woman with hereditary defects of the system of hemostasis are 18 times higher than in a pregnant woman without such defects. And this relationship is, again, statistically significant because we also look at a confidence interval. If one does not fall within this confidence interval, it means that our dependence is statistically significant. And if lower bound turns out to be less than 1, then that value is statistically insignificant because 1 is within the confidence interval. But in the case of a prospective study, such as a cohort study, we calculate relative risk. It was a retrospective study, yeah, case control, yeah, case. This is relative risk. Relative risk we should use when we have a prospective study or cohort study, maybe. We calculate relative risk. What is about relative risk? Relative risk is the ratio of the frequency of outcomes among subjects who were influenced by the factor under study to the frequency of outcomes among subjects who were not influenced by that factor. So, again, we have a 2x2 contingency table. Relative risk. Those who were exposed to the factor and the risk of those who were not exposed to the factor. You have the formula for calculating relative risk. Yeah? What is about relative risk? Again, the very big formula, but it's very, very simple formula. So, let's continue. And again, we must say when we can use the relative risk. It's used to compare the probability of an outcome depending on the presence or absence of a risk factor. For example, estimating the effect of smoking on the incidence of hypertension, for example. The conditions for applications are as follows. Again, we have the special conditions when we calculate relative risk. When? Firstly, data must be nominal. Use only 2x2 tables and binary variables, and prospective studies, such as cohort studies. Again, to generalize everything to the population, we need to specify not only the relative risk, but also the limits of the 95% confidence interval. Using the formulas on the slide, again, we have a relative risk formula. we calculate limits. These limits, lower limits and upper limit. The difference again is only the sign minus again, minus and plus. So again, let's look example for relative risk. We are given a prospective study. The sample consists of people who smoke and people who have never smoked. Watching them for 10 years to see if they developed a myocardial infarction, or heart attack, you can say. So, smoking, yes, no, and myocardial infarction by 10 years, yes or not. Okay, the samples are presented large on the slide, We calculate a relative risk. We have large numbers, you can see, these large numbers. So, how can we calculate relative risk according to this formula, Multiplied A by C plus D and divided by this result of C multiplied by A plus B. So, let's see. In this result here, A is here. C is what? C is here. D, what is about D? C plus D, C plus D. We have after that the result of C plus D here and here, And after that, C here plus the result of A plus B of this line, So, let's see, we get about 2. This is the relative risk. If we calculate the confidence interval bounds, the lower bound turns out to be 1.6, you can see, as a result of this calculation. And upper bound turns out to be 2.49 or 2.5, we can say, This is what? This is upper bound and the result of this formula, calculation of this formula. We write down the results. The relative risk is 2, the 95% confidence interval and limits. Let's see. Relative risk. 95 confidence interval and limits. Down limits and upper limits. And from this, we can conclude that a middle-aged man who has even smoked is twice as likely to suffer a myocardial infarction in the next 10 years as a non-smoking man. Let's see. 1 is not in the confidence interval, so the correlation that the risk is twice as high is statistically significant. And the conclusion speaks for itself. Smoking really is bad for you, students. Smoking really is bad for you. Now, after this, we should summarize the information on the analysis of qualitative data. When we are analyzing qualitative data, it's important for us to know if the samples are dependent or not. Firstly, we see dependent or independent samples. After that, because why we should know it? Because based on that, we will choose the appropriate criterion. If the tables are 2 by 2, then in addition to specifying the value of the criterion, we have to specify the odds ratio for the retrospective study and relative risk for the prospective study, for example. And on our part, on our course, we only said about number of independent samples. Yes, if we have independent samples. Dependent samples is not our course. So it was what? This was the analyzing of our samples. What is the next? Now let's move on to a discussion of correlation. Next part of our lecture is correlation. So, what is correlation? What is about correlation dependence? Suppose we have two random variables, x and y, that are affected by random factors. If variable x is affected by random factors a, b, c, and value y is affected by random factors a, b, d, then we say that there is a statistical relationship between the quantities. Statistical dependence is a dependence in which a change in one quantity entails a change in the distribution of another quantity. A special case of statistical dependence is correlation dependence. And so, it's the correlation dependence that we are interested in, really. It's more interesting for us, correlation dependence. What is correlation dependence? We must know it. Correlation dependence is a relationship in which a change in one variable leads to a change in the mean of another variable. Correlation analysis deals with the degree of relationship, closeness of relationship, we can say, between two variables x and y. Let's take the example of the baby's age in month and heart rate per minute. If we draw a scatter diagram, like as in this example, where the dots are each patient, these points, this is each patient, we can see that an increase in age, and on average, leads to a decrease in heart rate. It's really like as in our life, more age, less heartbeat, for example, heart rate. So increase age, decrease heart rate. It's very important to understand and know that having a correlation does not mean causation. Really, main idea, For example, a correlation was previously found between taking hormone replacement therapy in women and the risk of coronary artery disease. After that study, it was recommended for a long time that women should take estrogen to reduce their risk of coronary artery disease. But in subsequent studies, this was not confirmed, and hormone replacement therapy to reduce the risk of coronary artery disease was no longer prescribed. A correlation was found, really correlation was between them, but there was no causal relationship between the characteristics. Also an example. A correlation was found between spending of science in the United States, you can see this first example, and suicide by hanging, for example. But this does not mean that if people started spending more money on science, then based on that there were more suicides by hanging, really. There is no connection. But for example, another example. A correlation has been found between cheese consumption and the risk of dying by suffocating in sheets, for example. Again, if you eat cheese, it will not cause your risk of dying by suffocating in the sheets to increase, really. This is another absurd connection. Really. This is a number of, for example, another absurd connection. This is the number of Nicolas Cage moves and the number of people drawing in the pool, in the swimming pool, for example. There is absolutely no cause and effect relationship. There is only correlation. You always have to be clear about whether it's just a correlation or whether there is a cause and effect. Correlation, it's not cause and effect. Correlation is correlation. Cause and effect is cause and effect. Don't forget about it, please. So, the closeness of this correlation is assessed by the correlation coefficient. The correlation coefficient, what is this? What is this? Yeah, we must see the definition. The correlation coefficient is a characteristic of the closeness of the correlation between the variables x and y. Again, there is a certain algorithm in which case we will use which correlation coefficient. We are going to look at just two: the Pearson correlation coefficient R and the Spearman correlation coefficient ρ. You can see maybe Pearson correlation or Spearman correlation. We consider the Pearson correlation coefficient when we have quantitative variables. What else? When assume a linear relationship only for normally distributed variables. And what else? And for samples with more than 20 items. In all other cases, we use the Spearman correlation coefficient. We use it when the data is not only quantitative, but an ordinal scale, for example, pain scale maybe, yeah, in medicine. There is no requirement for a normal distribution when the sample is small, when the relationship is non-linear. But if there is a normal distribution in our case, it's still more correct to use those criteria and that correlation coefficient, which is designed for a normal distribution because it's more powerful, really. We look at a closeness of the relationship using a Cheddak scale depending on the value of the correlation coefficient modulus, absolute value of a correlation coefficient. In general, the correlation coefficient is a value that lies in the range of -1 to +1. If you suddenly get a coefficient value greater than 1, maybe 1.5 or 10 or 55, or if you suddenly get a coefficient value less than -1, for example, -5, -1.5, for example, in your calculations, then you have an error in your calculations. Find the mistake, please, for example. If you get a positive correlation coefficient from 0 to +1, then we can say that the relationship between the variables is direct. So, an increase in one of the values leads to an increase in the other, or decrease in one of the values leads to decrease in the other. Linear connection, we can say. Linear connection. If the correlation coefficients turns out to be negative from -1 to 0, then we say that the relationship is negative. Or maybe you can use inverse relationship, but you can see this word in medicine studies. It's not right, students. Please, I recommend to use only the word negative. When an increase, what is this? When an increase in one variable leads to decrease in another variable, and vice versa. Increase one, decrease second. Decrease one, increase second. This is negative connection. If it turns out that the correlation coefficient is 0, it may be 2. Then this means that the quantities are independent. What else? There is no connection. There is no connection between quantities, we can say. Also remember that the correlation coefficient is a dimensionless value. It's just a number that shows the closeness of the relationship between the variables. The closeness of the relationship is rated on the Cheddak scale from weak to very strong depending on the modulus, or we can say absolute value of a correlation coefficient, like as you see in this table. If we have a correlation coefficient, absolute value of correlation coefficient is less than 0.3, we can say that the connection is weak. If our correlation coefficient, absolute value of our correlation coefficient is more than 0.3 but less than 0.5, we can say moderate connection. If our absolute value of correlation coefficient is more than 0.5 but less than 0.7, we can say significant, noticeable connection. Next is, if absolute value of a correlation coefficient is more than 0.7 but less than 0.9, it's strong connection. And last, when absolute value of correlation coefficient is more than 0.9 but less than 1 is, connection will be strong, very strong, not strong, very strong connection. So initially, the closeness of the relationship and the direction of dependence can be inferred by plotting a scatter plot, also called correlation field, we can say. The first graph, this graph, shows that the correlation coefficient is minus 0.97 if we use a rounding rule, and we can see that the values are close to a certain straight line. We can see a certain straight line near this line, and we assume that there is a linear relationship, a very strong dependence and negative. In the second graph, for example, this is we assume a strong positive relationship, and correlation coefficient confirm this. This is positive, more than 0.9 absolute value of this more than 0.9, we can say very strong connection and positive connection because lines go up. So in the third graph, the correlation coefficient is negative and minus 0.43, if we use rounding rule. The points are very scattered, you can see. Not near, and the relationship is moderately negative. And in the last graph, we can see that the relationship is positive and correlation coefficient is 0.68, and the relationship is significant, but what? But not strong, not strong. So the Pearson correlation coefficient is calculated using this formula. Again, students, the formula is very, very, very large, but it's actually very clear. Again, let's look at an example for best understanding Pearson's coefficient. Pearson's correlation and correlation coefficient. Variable x. What is about variable x we have? This is the age of child in months, and variable y is number of urinations per day. So there is a table on the slide where our x and y data are placed here in here column and in this column. Let's look at the formula with you. In order to calculate the correlation coefficient, we need the product of sum of x, sum of y, a sum of multiplying x, y, and the sum of square numbers of y and x. And in the table, all the sums we need for calculations. These sums we need. and put it in big formula. We substitute these numbers, and what is about n? You can see n. What is about n? N is the number of elements in the sample. In our example, we have 10 numbers, so it's 10, you can see. Let me remind you that if we have less than 20 elements in the sample, we can't calculate Pearson's correlation, how I said earlier. But in this case, just an example to make it convenient for you, to show you all the information on the slide, really, only for best understanding. But remember, for Pearson correlation coefficient, we can't use the samples when we have more than 20 items here in sample, for example. In this case, this is only a learning task. We substituted all of our values into the formula, and the resulting correlation coefficient is about minus 0.94. Negative, connection, we can say. We got the Pearson correlation coefficient based on our sample. In order for us to generalize the result to the population, we also need to specify a confidence interval for this coefficient. Like as usually, we after calculation coefficient, after that we must know confidence interval, our mistake, for example. So after when we calculate the correlation coefficient, we must calculate the what? We must calculate the confidence interval. Confidence interval, students, formula for confidence interval is very scary, and I don't use in my lecture this, and only I can say to you that after the calculation, the coefficient and critical value for our example will be 1.96, and so after that we must calculate the upper and boundaries, for example, and the result of lower bound is minus 0.98 and upper bound is 0.75. Our correlation coefficient should lie in the range, because our number is minus 1.74, but for previous example will be plus 1.96. And we can say that our correlation coefficient should lie in the range between minus 0. And between our boundaries. And if you have something wrong, it means that there is an error in your calculations. But so further, we calculated a correlation coefficient. We have indicated the confidence interval. It's also very important to test hypotheses about the significance of this correlation coefficient, because there is a still possibility that our identified relationship is random. And in fact, in the population, these quantities are independent. So we test the hypothesis that about significance of this correlation coefficient. The null hypothesis tells us that R is 0. Alternative hypothesis is that R is not equal 0. You can see null hypothesis and alternative hypothesis. After that, we calculate the control value using the formula on the slide, using this formula, where R is correlation coefficient. What is about N? N again is the sample size. What is the next? Then we look at the critical values of the student coefficient from the distribution table with n minus 2 degrees of freedom. After that, we should compare our control value and critical value from table. The algorithm for testing the hypothesis is standard. as we discussed in the last lecture and today. Let's calculate the control value for our correlation coefficient from the example. You can see approximately, we have a 7.2 using correlation coefficient, positive number of correlation coefficient, and using 1. We have 10 numbers, 10 items in our samples. Then we should look in students' distribution tables for the critical values for the 0.05 and 0.01 significance level for the 8 degrees of freedom, because degrees of freedom will be 8, n minus 2, 10 minus 2 is 8. The critical value for the 0.05 significance level is 2.31. And critical value for the 0.01 significance level is 3.36. Our value is 7.8. We have 7.8. Really, 7.8 is greater than these numbers. So we see that our value lies within the realm of significance with a 99% confidence level. And what is this? It turns out that we should reject the null hypothesis. And we can say that with a 99% confidence level, the relationship between the variables is statistically significant. That is, it's not random. This means that there is the relationship, or relationship is there. So it was Pearson's correlation. We in our practice we will calculate the Pearson's criterion, use the Pearson's correlation and calculate the correlation coefficient and analyze it in our data. So now let's discuss the Spearman correlation with you. Spearman correlation is rank correlation. And Spearman's rank correlation coefficient is the non-parametric counterpart of Pearson's coefficient. It applies when there is no normal distribution, when the data is not quantitative, but ordinal scale on small samples. This coefficient is ranked. So you and I will be ranking again like as in previous lecture. The Spearman correlation coefficient ρ, this is the Greek letter ρ, students, not P, this is Greek letter ρ, is calculated using this formula. In the formula, what is about n? Again, n is the sample size. And what is about di? This value di. Di is a rank difference. Let's look at an example again. The example is the same as before, where x value is the child's age in month and y value is the number of urinations per day. For each value of x and for each value of y, we need to rank. How can we do this? Firstly, let's start with the value of x. Let's start with the value of x. We are ranking the value of x from lesser to greater, from the smallest to the largest. Let me remind you that rank is an ordinal number in an ordered sample. Firstly, we must put our x value, we must put ordinary numbers, so order our items. And only after that we can use a ranked. So, item 1, first ordered number, item is 1, rank will be 1 because the rank is what? Is an ordinal number in ordered sample. Item 2, ordinal number 2, rank is 2. Next, then there are two identical values, 4 and 4. What happened? Their ordinal number is 3 and 4. And let's remember, if we have this situation, the rank will be the arithmetic mean between the ordinal numbers of the same values. So, ordinal numbers 3 plus 4 divided by 2. This is the average mean, and this is a rank will be 3.5 for every number. Rank will be 3.5 for every number. Then we again have the same values, 6 and 6. What happened? Again, we must calculate average mean between ordinal number 5 and 6. What happened? 5 plus 6 divided by 2 will be 5.5. So, the rank will be arithmetic mean is 5.5. And then there are no repeated values, you can see 8, 10, 11 and 12, and will be the same rank will be the same value like as item. So and will be the same calculations with value y, yeah, the same calculations with value y. First, we order our values from the smallest to the largest and arrange the ranks according to the same rule. The same number if we have non-repeated numbers, and average value of the items, yeah, average value of the items. So after that, after we have ranked the values x and y, what is the next? We go back to the table. Write to each x its rank and to each y its rank. Yeah, let's see. But we must be very it's very, students, let's see. This is the ordinal numbers, yeah? But in the table, our numbers stay not ordinary. And be careful with the ranks. We must put this, the rank for the number, Be careful with this. After putting ranks, what happens? Ranks for x value and for y value, we must calculate or refine the difference of the ranks and put it in square. This rank difference. So we find after we put rank difference in square, we should summarize the last column, and which is the sum of squares, yeah, of rank differences, yeah. Substitute this value into our formula and calculate the Spearman correlation coefficient. In our example, it will be minus 0.92. Minus 0.92. What is after? After after we have calculated the Spearman correlation coefficient, we must test the hypothesis that the Spearman correlation coefficient is significant, because the identified relationship may be random. The algorithm here is slightly different. We compare the absolute values of the Spearman correlation coefficient with the critical values. It's calculated using the formula that listed, yeah, you can see. We should calculate the critical value. In this formula, what is about T alpha L? T alpha L are the student coefficient from the student table, where alpha is the level of significance and L is the number of degrees of freedom. In this example, again, it's n minus 2. And what is about n? N again is the sample size. Let's substitute our previously obtained values into this formula and we get the critical value at the significance level of 0.05 will be 0.32. We should calculate it, yeah? And at a significance level of 0.01, the critical value will be 0.47, according to this formula and these calculations. Our correlation coefficient, our absolute value of correlation coefficient lies in the area to the right. Because our correlation coefficient is more than both of these values. So, and this is area of significance with a 99% confidence level. And what is this? It turns out that we should reject the null hypothesis, and we can say that with a 99% confidence level, the rank correlation between the variables is statistically significant. That is, it's not random or non-random, we can say. And it was the correlation, Spearman correlation, yeah? And the last thing you and I should consider is regression analysis. What is this? What is this words, yeah? Regression analysis is the method of investigating and modeling the relationship between variables when one or more variables predict another. Regression analysis is used to predict the value of some random variable. And in the case of simple linear regression, where a linear relationship is y is a plus bx, where x is an independent variable, we can say this is a predictor, and y is a dependent variable, predict value. What is about a and b in this linear? And this is coefficients of the linear function. Sample estimates of the general parameters alpha and beta, which determine the regression line in the population. To generalize to the population, we need to construct a confidence interval for this line. Again, the coefficients a and b are calculated using the methods of least squares. The method is that the sum of the squares of the residuals must be minimal. The points on the coordinate system are our values. The line is chosen so that the difference between observed y and the value of y that we assume on the line, that is so that the sum of these residuals is minimal. Consider the conditions of applications of linear regression analysis. Again, yes, there is a special application conditions. What is this? It can only be used when the dependent and independent variables are quantitative. Again, also the relationship between x and y is linear. It's mandatory that the observations in the sample must be independent. Only one pair for observations for each patient. It's also important that the residuals of the difference have a normal distribution and a constant variance for all predict values of y. So, again, let's see the example for best understanding linear regression analysis. Our same sample where x value is child's age in months and y value is the number of urinations per day. Let's build our function. To do this, we need to find coefficients a and b Y we have, X we have, but what is about A and B? We should calculate it according formulas. Formulas for finding these coefficients are shown here. These formulas. Let's substitute our sums from the table into these formulas. Again, we should put summarizing of multiplication x and y, summarize of x value, y value, squares again. And according to these formulas, our results are that the coefficient of b is minus 1.04 and coefficient of a is 24.94. So, if we plot our straight line on the scatter diagram, it goes about midway between our points. That's correct, If the line goes above the points or below the points, for example, maybe here or here, according our points, what happened? There is an error in the calculations, and we should find this mistake and calculate again and draw again. From this straight line, we can make some predictions. For example, we can say that at 9 months of age, the child has 17 urinations per unit. For example, here. We can also estimate the regression model by the R-square coefficient, which is the correlation coefficient squared. It's called the coefficient of determination and shows the proportion, what percentage, of the variance of y that can be explained by the relationship with x. This is in the case where we have one variable, a simple regression analysis. But there may be cases where we don't have one variable, but severe. For example, the number of pieces per day can depend not only on age, but also, for example, on the amount of water drink per day, for example, water drunk. That it turns out that there is no one x, but x1 and x2. This will be called a multiple regression, we can say. And there can also be a variant when the dependent variable y takes only binary values, so maybe 0 or 1. There is a disease or there is no disease, for example, like as a code. Then this is called logistic regression. It allows us to calculate the probability of disease development depending on some factors. But there are more complicated methods and they are not part of our first course curriculum. So, today I can say you thank you for your attention and goodbye.